Hello, everyone. I am very delighted to join you today at this special Global XR event. I am Iman, a PhD and engineer in mechanical engineering education. My research work revolves around improving engineering education. Education, particularly engineering education, is my passion. So during my own training as a mechanical engineer, I have encountered many constraints that drove me to make an impact and trying to contribute to enhancing the training of the next generation of engineers. So, over the past 6 years, I've been involved in teaching and tutoring engineering students. I have endeavored to implement the findings of my research to foster their creativity and innovation. And today, I'm continuing my research in this field with a heightened focus on the new technologies and especially immersive technology. It is true that interactive and immersive technology is an emerging technology that is promising for the engineering education and training. It represents a tool that can create a pipeline for cooperation with industry to prepare the next generation of graduate engineering with the skills required for business. But, with this, at the same time, we can have some questions about the dark side of these immersive technologies. And we are thinking about all the drawbacks and their negative impact that can influence the way engineering students or any kind of students they are learning and they are socializing and working within a team. That's why we ask this question: how can immersive technology revolutionize the way we learn and teach, and what challenges do we need to overcome to fully harness its potential in education? During this presentation, we'll start with an overview of the use of immersive technologies in education with the focus on higher education. Then we'll talk about aspects of the application of immersive technologies in engineering education, which we will illustrate in the following section with several case studies, and we will then discuss a little bit the results and conclude with a look ahead to future perspectives. Let's start with a brief reminder of the fundamental concepts of immersive technologies. The first concept is virtual reality, which refers to a computer generated environment that simulates a real or imagined world, providing an immersive 3D experience to the user. In VR, users are completely immersed in a digital environment, typically using a head mounted display or VR headset, which tracks their head movements to make the virtual environment respond in real time. It often includes auditory and visual feedback to create a sense of presence. Then we find the augmented reality, which is a technology that overlays digital information such as images, videos, 3D models, or text onto the real world, enhancing the user's perception of their physical surroundings. AR is typically experienced through smartphones and within many applications like Snapchat and all applications using filters, tablets, smart glasses, or heads up displays, allowing users to interact with both the physical and digital worlds at the same time. Next, we find mixed reality, which is a technology that combines aspects of both the physical and digital worlds to create a new reality where digital and physical objects coexist and interact in real time. So the mixed reality blends elements of both AR and VR, allowing digital objects to be anchored in the physical world and interact with it. This technology often employs headsets such as Microsoft HoloLens to overlay digital content onto the user's real world view. And finally, we find extended reality, which is an umbrella term that encompasses virtual reality, augmented reality, and mixed reality. It refers to a spectrum of immersive technologies that merge the physical and digital worlds to varying degrees, providing a continuum of experiences. XR is a flexible term that can describe any technology that combines aspects of VR, AR, or MR. According to a human centered definition, the XR are based on the three I's. The first I is interaction, where the user can interact with dynamic world and objects, responds to uh, his environment through reactions, gestures, verbal commands, and communication. The second I is imagination. So in the XR, the human can explore the world, the digital world, through his imagination, create a virtual world, and solve problems inside this imaginary world. And the third eye is the immersion. So here the user is immersed, totally immersed in a digital world with digital graphic simulations. He can create some realistic environments, landscapes, objects, and interact with them. And he can also make decisions and make some actions that leads to results. The XR and virtual world are gradually becoming an essential part of modern academic education and an achievable alternative in comparison to the traditional learning. These technologies promote learning by doing or experiential learning, known to be one of the best ways of skills acquisition. XR technologies offer diverse opportunities for research and innovation by providing immersive, interactive environments for experimentation, data analysis, and creative exploration across a wide range of disciplines and industries. Researchers can use the XR to visualize complex scientific data and simulations in 3D. So this aids in data analysis, allowing for deeper insights and the discovery of patterns and anomalies that may not be evident in traditional 2D representations. So the XR can even be applied in social science research for studying human interactions, social behavior, and the impact of different environments on social dynamics. So the applications of XR in the research are very, very wide, and we can't cite all of the examples. Then we find the applications of XR in engineering education. So here we can find a lot of aspects of this application. So they can be used to create immersive and interactive learning environments. XR allows students to explore and manipulate complex engineering systems, conduct virtual experiments, and simulate real-world scenarios. It enables hands-on skill development, facilitates interactive 3D modeling and design, and offer practical training in areas. So the XR can also promote interdisciplinary collaboration, enhancing problem-solving skills and fostering a deeper understanding of engineering concepts, making a valuable tool for modern engineering education. Besides, we can also find a very wide application of XR in the medicine education. So here, XR can be used to help students in medicine to make some surgical training. So here, XR can provide realistic surgical simulations for medical students and professionals. Surgeons can practice procedures, hone their skills, and improve hand-eye coordination in a safe virtual environment. We have also the application within the libraries. So today there is so many virtual libraries and archives inside the traditional libraries. And here we can use these technologies to create virtual libraries, allowing students to explore historical documents, manuscripts, and rare books in a digital environment. XR technologies can also be used widely in vocational training, and here it can be used for innovation and also workforce development. So it can be used to train workers in a variety of fields, from healthcare to manufacturing and construction, and to develop innovative training programs that improve skills and productivity. And here, learners can practice potentially hazardous tasks safely. And last but not least, um, we can find XR applications in archaeological reconstructions. So archaeologists can use XR to reconstruct ancient sites and artifacts, allowing for more accurate analysis of historical objects and locations. Researchers can virtually explore archaeological sites and make new discoveries. So let's detail these VR devices that we have just presented. So here we can find two groups or two types of devices which depend on the cost. We find low cost VR devices like the Google Cardboard, Samsung Gear VR, and these equipment can't only be used inside laboratories in higher education, but so, in order to implement the XR technologies inside the universities and laboratories and integrate these technology inside the curriculum, there is plenty of digital content, tools, and assets that can be utilized in a virtual, digital, or even real environment. So these virtual resources are divided into visualization types, um, which are not immersive, and we can find the conventional peripheral. So here we can also use some softwares that can allow simulation, creation of some digital environments, and there is also some specific devices. So here we can find some projectors and special screens. On the other side, we find interaction devices, and here these are the equipment that we can use to be immersed inside the environment that had been created. And here we can find the head-mounted display or the virtual headset, and also we can find the virtual caves. So here are some benefits of the XR implementation inside higher education. We can find that these technologies can enhance learning experience by creating an engaging and interactive learning environments. And it can improve the learning of students, especially practical learning, because students can gain practical experience in a safe and controlled virtual environment. For example, the medical students, archaeology, and other students can explore some experiences that can be sometimes impossible in the reality. We can find also the global collaboration, because these technologies enable international collaboration among students and researchers in some open environments learning. We can find also the benefits on innovation and research. We find also inclusivity, because these technologies help students with disabilities, or for example some students with some mental health problems, or that can have some difficulties of learning. And uh, one of the important benefits, especially for institutions and laboratories, is the cost saving. So in some cases, immersive technologies can reduce the cost associated with physical resources and travel. So virtual labs and virtual field trips can be more cost effective. On the other hand, higher education institutions may face some challenges when trying to implement these technologies. Firstly, we find cost of implementation. So setting up and maintaining immersive technologies can be very expensive, including the cost of equipment, software, and ongoing maintenance. We find also the difficulty of content development. So here, creating high quality immersive content is time consuming and often requires specialized expertise, which can be a real challenge for the universities. And here, automatically, we speak about technical issues. So technical glitches, hardware limitations, and software compatibility can disrupt the learning experience. We find also the training of educators and student use of these XR technologies. And here, not all instructors may be familiar with these tools, even if they can be software professors, or, for example, some researchers in this field. Because here we need some new skills, and the most important thing is the pedagogical abilities and how to be able to use these technologies in order to help students to learn and acquire new skills. Students and educators can also be exposed to some ethical concerns like privacy issues, data security, and ethical considerations in these virtual spaces. And universities need policies and guidelines to address these concerns, and that's why there is today some standards that had been recently published in order to create a frame and to create some laws for the implementations and the use of these technologies in the educational field. And we find also the accessibility. So here there is a problem because not all students may have access to the necessary hardware or the physical space required for immersive experiences. Another important issue is the integration inside the curriculum. So here, in order to successfully integrating immersive technologies into the curriculum. And finally, we find the content overload. So here, sometimes using a lot of technologies can be overwhelming for some students and leading to potential distraction and cognitive overload, and sometimes even creating some mental or health problems. So let's start from a macro and a global vision about what's going in the world and link it to the use of XR in engineering education. So let's start from the industry 5.0, which represents a highly interconnected and data-driven ecosystem where cyber, physical systems, and human-machine collaboration play a central role. So, in this context, engineers must possess skills that go beyond traditional engineering knowledge. They need to harness the potential of emerging technologies like virtual reality to optimize processes, foster innovation, and deliver outstanding products and services. So, by integrating virtual reality into engineering, education, and training, we bridge the gap between conventional engineering practices and the demands of Industry 5.0. So the virtual reality serves as a pivotal component in the transition to Industry 5.0 as it enhances the skill set of engineers to meet the evolving demands of this advanced industrial era. So this integration equips engineers with the proficiency to navigate digital twin systems, augmented reality interfaces, and collaborative robotics. They become adept at using virtual reality not only as a design and training tool, but also as a means to streamline manufacturing processes and create smart, interconnected factories. Industry relies on distinctive skills to innovate and compete. Thus, it is essential for educational institutes to prepare for emerging technology in both infrastructures and policies. The implementation of XR in engineering education is not limited to the visualization of virtual environments inside classrooms, but also to the creation of a totally or partially virtual laboratories. Virtual laboratories in engineering education are digital environments that replicate physical laboratory settings and equipment for the purpose of teaching and learning engineering concepts and conducting experiments. So these labs leverage XR technologies to create immersive and interactive experiences for engineering students, simulating real-world laboratory experiments and scenarios. So these laboratories are designed to improve the students' ability to investigate and solve engineering problems with appropriate levels of independent thoughts and creativity, and also to demonstrate suitable levels of reporting, technical information, and analysis. Virtual labs can have many benefits on both students and institutions. First, they can ensure a positive impact on learning processes, cognitive development, and pedagogy. They can also help to have a better understanding of complex technical concepts and ability to develop conceptual models. They can also ensure an improvement of the technical skills of the students. They can create the opportunity to implement some difficult or impossible experiences in engineering education institutions. And here we can have the example of clean rooms, like the clean rooms where we can create some composite materials. So here costs of devices, energy, materials, and people are very high. And we need skilled personnel in order to implement like these clean rooms inside institutions, and only a certain number of people can be present in these clean rooms. So here students and teachers, by implementing a virtual clean room, don't have to worry about damaging the devices and destroying samples, and many more experiments can be accomplished in short time, and at the same time they will learn a lot about how to make the maintenance inside the clean rooms, how to ensure safety, and how to manipulate the equipments. We have also the possibility of successful insertion of former students into the industrial sector in the future after their graduation. And last but not least, we can have an assimilation of knowledge about new techniques for specific industries like the automotive, aerospace, and aeronautic industries. Both students and educators can have many aspects of interactions inside a virtual lab, like moving around. So here students can explore the virtual environment, whether by flying, teleporting, or walking. um, they can um, so we have also the user generated content. That means that students can create new content such as 3D models and upload that new content to the virtual environment. We have the assembling. So students can select virtual objects and place them together in order to create new objects. We have also the passive observation. So here students can only visualize some experiments and look around the virtual environment. So here it can apply to the applications where user can travel predefined paths and look around while doing so. We can find also the creation of new instructions. So here the students have access to a tutorial or instructions on how to use the VR application and how to perform the learning task. And here these instructions can be given by text, audio, or virtual agent. And finally, we find interaction with objects. And here students can select virtual objects and interact with them in different ways. These includes retrieving information about an object in written or spoken form, picking and rotating, zooming in on objects to see more details, and changing an object's color or shape. So in order to illustrate these information and facts, which may seem theoretical, we will present in this section the results of some scientific publications detailing some case studies of virtual laboratory setups in different engineering fields. Of course, there are a huge number of XR labs using many equipment and many XR technologies in engineering training around the world, but time does not allow us to present them all. So let's start with the first experience. It's the German experience. So a virtual reality practical course had been implemented inside the laboratories of the Life Cycle Engineering Solution Center in the Institute of Information Management in Engineering at the Karlsruhe Institute of Technology, KIT. So here a group of 15 graduate and undergraduate students from mechanical engineering, mechatronics, electrical engineering, computer science, physics, or engineering management participated in this experience by creating a model and then simulating it using a VR lab. So here many tools and materials had been used. inside the VR lab, which was equipped with high-end virtual reality environment, distributed stereoscopic visualization in a three-sided cave setup, a mobile power wall, and two haptic devices, an RT tracking system for head tracking, and a flit stick for interaction, and other equipments like 3D monitors, HMDs, depth cameras, data gloves, and some other smartphone. So many softwares had been used and combined to these tools, especially the 3D VIA virtuals of Dassault systems, and then the group or this the experiment team had created their own virtual reality engine, PolyVR, based on an open source libraries like OpenGL and using the C++ programming language. At the end of this experiment, 4 projects had been created. The first project was the drive prototype with a seat box, where students build a seat box with a real car seat and use the gaming controller as a car interface. They like the steering wheel, the pedals, and the gear. So the students had to implement a virtual world which contained a 3D model of the car, a track, the environment, weather conditions, and sound. So the most important part was the driving simulation and physics, for example, the collision detection and some problems related to the balance of the wheels. So here, another project was a little bit similar to this one, but with a real car. So a car was given by a company, and students used this car to replace the seat box, but in this case they had to link the car system, driving system, to the 3D environments that they have created. The third project was Energy Experience Simulator, where they had to simulate the use and the waste and the economy of energy. And the last application developed by the students was the Immersive Car Cockpit Simulator. So during this project, students created a simulator that can configure the parameters of the cockpit, change the characteristics, colors, and even control the dimensions. According to this scientific paper, here are some success factors of this project. Firstly, the use of a modular open source software which helped the students to create 3D models and to code some parameters and to code their own software freely. Secondly, it's important to encourage creativity and innovation among students in order to help them to generate some creative ideas. And efficient project management and planification was very important in order to ensure a positive progress of the project, as well as a respect of the time for every task. Then come the team's multidisciplinarity. So here, one of the strength of this team was that it was composed of many of students from different fields like the engineering, the mechanical, electrical engineering, as well as management. And finally, the task design. That means that everyone of the team knows his tasks and what is the deadline and what are the objectives. At the same time, this team faced many challenges, like some challenging experience for students. Um, that means some part of the project was very difficult to deal with. Secondly, keeping students motivated and engaged until the end of the project, and the time management. The paper suggested some solutions in order to improve this experience in the future years, like the clarity of project objectives and outcomes from the beginning of the project, and the courses and content updates every semester in order to help students stay motivated and interested in the XR technologies. The second experience took place in Mexico, and especially in the Universidad Popular Autónoma del Estado de Puebla, the UPAEP. Um, the experience was organized by the Industrial Engineering and Automotive Design Department. So, a group of students specialized in electronics, mechatronics, and automotive and industrial engineering. So, the implementation of these guidelines and the standard aim at the creation of a safer virtual and blended labs. The second experience took place in the University of Autónoma del Estado de Puebla in Mexico, where a group of industrial engineering and automotive design students specialized in electronics, mechatronics, and automotive and industrial engineering created a number of projects using a VR lab. So, in this VR lab, many tools and materials were used, like digital technology sites and infrastructures dedicated to VR and AR learning, a VR headset and AR headset, um, and these materials were combined with some softwares like the 3D design softwares, as well as additive manufacturing, and some 3D printers had been used, like the 3D printer Mark Forged and 3D printer Formlabs high resolution, as well as some softwares like Digital Technologies and HPZ Book. What's important and very interesting in this experience is the use or the implementation of the standard ISO IECTR 2384-1, which was published in 2020. So, why this standard was published? Well, however, the use of VR and AR technologies for industrial and educational activities requires some important guidelines and protocols. Um, so, this standard was released in 2020 as a standard establishing these guidelines on information technology for education and training based on the use and creation of the VR content and application. So these guidelines are aimed to prevent issues associated with the use and development of VR technology and content, such as the discomfort caused when actual physical movement does not occur with respect to the visual stimulus generated in the virtual environment, and the eyesight problems due to the proximity of the VR hardware to the user's eyes, as well as the photosensitivity syndrome, where seizures occur due to rapid flashing light stimuli. We can also speak about some muscular disorders due to performing repetitive tasks over long periods of time, and some hygiene problems due to the poor disinfection or cleaning of the VR hardware. And we can add to this the accidents like collision, falling, caused by the limitation of the user's field of view when using the VR devices. The results of this experience were two projects. Firstly, we find the automotive design testing. So it's a blended lab where the objective is to test the dimension as well as the mechanical characteristic of a prototype. And the second project is the digital and virtual validation of the Formula SAE project. And here students aim at creating a prototype of a formula, and which they want to use in order to participate in an international competition. According to this study, the key success factors of this project are: firstly, the fully open, reconfigurable, and obstacle-free spaces with safety and hygiene guidelines for the VR and the AR interactions, thanks to the implementation of the ISO standard. And secondly, the combination of different CAD technologies and conventional computer laboratories in different areas of engineering. At the same time, the different members of the project, either the students or the educators, faced many challenges. First, we find the lack of guidance regarding the use of XR technologies, the limited budget for financing larger facilities and technological resources, then the scheduling and pedagogical conflicts when introducing new content and skills into the educational programs, and finally, the resistance to change from the traditional pedagogical practices from the students or from the other educators or some people who are working in the practical works laboratories. Our last experience was held in England, and is particularly in the Warwick University. So here the project was realized by a group of mechanical engineering students inside the institution of mechanical engineers and with collaboration of Metrology Center of Excellence. The aim of this project was the implementation of the FVPA process which means final vehicle product audit. This is a process that aims to assess the product in the initial design stages to evaluate customer requirements and convert them from subjective measures into objective ones. So here the objective is to train students to acquire the skills in order to be able in the future to evaluate a real world product for one of the industrial partners of the university. So in order to complete and accomplish this project, a VR lab was created based on a number of tools and materials like the IR cameras, control desks, 3D glasses, speakers, projectors, and the NVIDIA plexes, as well as some XRA and laser scanning. These equipments were linked to some softwares, especially the 3D CAD softwares and the ORDesk showcase. And here we find some of the results of the project. So firstly, the teamwork of this project was able to create their own virtual lab based on a number of 3D virtual reality equipments, and it's a whole system. So in the first picture you can see all the equipments and the softwares linked, and the relationship between every equipment. And in the second picture, you can see here the students while working and implementing the FVPA audit project. So you can see on the screen there is a picture of a car, and they are using the HMD equipment in order to make the measurements and make the metrology controls on the vehicle. At the end of the project, the engineering students succeeded to create a virtual experiment and training system and to implement it. So this project imitates various kinds of real-life engineering challenges that cannot be produced in the reality. According to the author, some key success factors of this project were: firstly, the focus on the combination of optimization, engineering, innovation, and mechanical and quality control. Secondly, the project planning and resource management. Then the learning attitude and lessons from previous projects. Successful product development and the launch using the NPA, that means new product introduction process, and the critical thinking and economical analysis. And the most relevant challenge that faced the whole team was the cost of the project. So, based on our analysis of the learning outcomes of these 3 experiments, we have summarized the skills acquired by the students and classified them into technical skills like the 3D modeling and design, simulation and analysis, programming and scripting, hardware and software integration skills, and the data visualization. We've also determined some soft skills like the collaboration, critical thinking, problem solving, and creativity, attention to details, time management, adaptability, and autonomy, as well as empathy and user-centered design. So the use of these virtual laboratories can therefore have a positive impact on future engineers, enabling them to develop skills that will facilitate their integration into the job market, or even better, to create their own innovative projects. Besides, universities and institutions can also benefit from this investment through, firstly, decreasing long-term asset costs by addressing training, equipment, time, and expenses. They can also reduce the use of hazardous materials in training and the environmental impact. They can also promote scientific research advances through more simulations and publications. These technologies can also promote inclusivity by allowing special needs engineering students to access some challenging environments. And the use of XR technologies can help to boost the institution's reputation by elevating students' learning experience. And finally, providing an effective platform for virtual labs in distance learning. Through our analysis of the literature review related to the implementation and experimentation of XR technologies in multiple institutions, we have identified some areas for further development. Firstly, in many studies, learning theories are often not considered during the design of the VR application, and a greater focus is put towards the design and usability of the VR application than the learning process. So, we think that a deep work needs to be done on the instructional and learning design of the courses, because that could hinders the objective of using VR in education to support and help students better understand their courses and maximize their learning. Furthermore, we noticed that there is a lack of detailed mapping of the targeted skills to be acquired by students, and an absence of studies aiming at linking the XR applications to the competency frameworks related to every field of engineering education. And now let's wrap up. So, as we've seen, the adoption of VR technologies demonstrates clear advantages for both students and educational institutions. It results in improved pedagogy and cognitive development, ultimately enhancing students' academic performance. So, this positive outcome is a direct result of aligning the VR application's design with specific learning objectives and theories. Furthermore, using VR to actively engage students embodies a student centered approach and aligns with the principles of blended learning approach and the approach of learning by doing, surpassing passive and traditional teaching methods. So, universities and institutions benefit from cost savings by replacing costly physical laboratories with VR alternatives and requiring less infrastructure for physical lab spaces. Additionally, it promotes safer working environments for students and positions institutions favorably in supporting VR for distance learning and students with specific needs, especially if some standards and norms are applied. So, despite the perceived limitations of this technology, careful design can address these issues effectively. So, VR stands as an innovative educational technology poised to reshape the future educational landscape significantly. In the near future, engineering students might use the XR technologies to collaborate on complex design projects internationally to promote open and collaborative innovation in multidisciplinary projects. Additionally, XR could enable students to explore cutting edge technologies like autonomous vehicles or smart city planning or even building stations in space. Finally, here is a list of biographical references used in this presentation. And I would like to thank the organizers of this conference for their efforts for gathering us today in this great event. And I would like to thank you for your attention and welcome your questions and comments.